Okay, so this is the continuation of the day 58 assignment, and we're going to wrap up with showing the electron configurations of a few elements. We'll do a few more of these in class on Monday. So let's go ahead and I talked at some length in the video notes. You should watch those, and also earlier in the this assignment about why this structure is the way it is. It's called the Aufbau structure for placing electrons, and it just shows the different energy levels. So if we go to the 1s, for example, we have hydrogen and helium, and so those two electrons would go right here. In the notes, I started by putting the down arrow on the left and the up arrow on the right. Usually it can be done either way, and that's the way I was taught. But actually, usually more conventional these days is to have the up arrow on the left. Okay, so the 1s orbital has 2 electrons, and what we are doing is boron. So the 1s orbital has 2 electrons, so boron has a full first orbital. First orbital is full. Now we go on to the second orbital, and the 2s is at a lower energy level than the 3 2p subshells, and that means we're going to fill this before we start filling any of these. You always fill lower completely up before you start filling anything higher. So boron would have another electron here in the 2s, and a down arrow in the 2s. Next, we're going to go now to the 2p, and boron, if you can see, is the first element in this section over here, which represents the p orbital. So it's going to have a single electron there, and that's all. Boron has an atomic number of 5, so it has 5 electrons, and that's how they are placed. So 1, 2, 3, 4, 5. All right, now how do you write the electron configuration for that? It has it has 2 electrons in the 1s orbital, so we write 1s and then a 2. It's not a squared, it's just symbolizing it. It represents that there's 2 electrons in that orbital. Next, you come here and there's a 2s, and that also has a 2. And then finally, it has 1 electron in the p orbital, in the 2p orbital. So you write 2p, and there's 1 electron. You don't write a separate p for px, py, and pz down here when you write the electron configuration. So that's the complete electron configuration for boron. Now we're going to do it using the condensed electron configuration. And what you do is you start with the noble gas that's on the previous row. So boron is in the second row, so you start with helium. And what you do is you put that noble gas in square brackets. So we put He like that. Next we go, and He is represented by a full 1s orbital. And then you go to the 2s orbital, so we write 2s2, just like we did above. And finally 2p1, and that's the condensed electron configuration. As you can see in this example, it's not any shorter than the regular electron, but as you get down lower and lower, further down on the periodic table, it'll make it a lot shorter if you use the condensed electron configuration. Okay, let's keep going, and now we're going to do aluminum. And down here somehow this got cut off, so you should write condensed electron configuration here. Alright, so we're at aluminum. So that is in the third row of the periodic table, and it's the first element in the p orbital here. So we're going to start by doing the first orbital, so it has a full first shell right there and right there. You now come, remember if you viewed the video, these two columns represent the s orbitals. So it has a an electron there, and an electron there. So that's the electron configuration of beryllium. Now we're coming over to the p orbital. Since aluminum is down in the third row, it's going to have a full 2p orbital. Watch how I draw these arrows though. Let's draw them in the proper order. So we filled up this because it was lower than 2p. We filled up 2s because it's lower than 2p. Now what we're going to do is we're going to draw an up arrow there. Now the next arrow is not the down arrow there. The electrons want to spread out between these three subshells before they start pairing up. So we're going to put another up arrow there and another up arrow there. This is called Hund's rule. Hund's rule states that the electrons want to spread out between the three subshells before they start pairing up. Now we need to fill up this second orbital because we need to get all the way up to 3p for aluminum. So now we're going to start pairing them up, and we're going to put a down arrow. The fact that an up arrow has to match up in the same subshell here with a down arrow is called the Pauli exclusion principle. And that simply means that electrons have to have opposite spins. Since they're both negatively charged, they repel each other. And but what offsets that repulsion, that idea that they want to push away from each other, is that they're spinning in opposite direction. And that makes them kind of somewhat want to attract each other. Not totally, but somewhat. And therefore that allows them to live together in the same subshell right there. So we're going to place this one, and then we're going to place this one, and then finally this. And when you have a full p orbital, as we do here, that represents a noble gas. In this case, this would represent neon. Right here. Okay, now, so we've completed the 2p orbital. Now we're going back to the 3s orbital, and there's two electrons that can fit in the 2s orbital. So one like that and one like that. You fill the 3s before you go to the 3p. So we filled sodium and magnesium, and now we go over to aluminum, and that's what we're shooting for here. And so it has a single up arrow right there, and that is the electron configuration for aluminum. So now let's write that out. So we have the 1s orbital, and we have two electrons in it, so we put the 2 there. Then we have the 2s orbital here. We have two electrons in the 2s, so we put a 2 there. Now we're off to the 3p, and as I said, you don't break this up into x, y, z. You simply write 3p, and there's a total of 1, 2, 3, 4, 5, 6 electrons there, so you put a 6 there. Now we're up to 3s. There's 1, 2 electrons in the 3s orbital. And finally, there's the 1 electron for aluminum in the 3p. And that is the electron configuration of aluminum. Now we're going to do it in condensed form. So rather than starting at 1s, we start at the noble gas in the previous row. So here's aluminum. So neon is the noble gas in the previous row. We showed that's right here on this diagram. So we put square brackets and an Ne. And now we just continue from there. We go up to 3s2 and 3p1. And that's the complete condensed electron configuration for aluminum. So these really aren't that hard. We'll go ahead and do a couple more. All right. So here we are with copper. So let's find copper. Copper is down here. And what we're going to do is start with the 1s orbital. So it's full. Copper has a full first orbital. Looks like that. You can just assume everything that's before this element right here is filled up, or everything that's before this row. So it's in the 4th row. It's actually the 3d orbital, but it's in the 4th row. So we're going to go ahead and fill up the 2s. And then our p orbital is going to be filled up completely, but rather than just fill in 6, do it in the proper order so you remember how it works. This is Hund's rule. So you spread the electrons out, and they're all up arrows at first. and then you go back and pair them up with down arrows. That's opposite spinning electrons. So again, here we are at neon. By the way, down here were with helium right there. So with the exception of the helium at the 1s orbital, the end of it, every filled p orbital is going to be a new noble gas. Okay, now we're at the 3s. We need to get down here to copper. We're at the 3s. It's sodium and magnesium. So we put an up arrow there and a down arrow there. Okay, next, we're still in the third row, third period, so we go up, 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 and then come back down, down, and down. So we'd have another filled p orbital. In this case, that would represent argon. Only s and p orbitals are valence orbitals. So when you get down to the transition metals in the fourth row, they are not valence electrons or valence orbitals. And now that's where we are. We're down in the fourth row with the 4s. So there's going to be one of these. Now I'm going to write this with pencil, and I want you to watch this. You needed to read your notes to know what's going to happen next. Not quite as obvious. First of all, you do 4s, and then remember that the order of electrons has to be s, p, d, and f. So any particular row has to build its orbitals in that order, s, p, d, and f. Well, here we have 4s. If right following 4s is a d orbital. The transition metals represent d orbitals. But the fourth row has not had its p orbital yet. It doesn't have its p orbital until over here. So somebody stuck a d orbital in there. What do you do with it? Who does that belong to? It cannot belong to the fourth row because the fourth row, as I said, has not had the p orbital yet. That has to belong to the third row. So just remember, the d orbital of a particular row actually appears one row below that particular row. So if you're talking about the third row, here's the 3s orbital right here. Here's the 3p orbital over here. Both are in the third row, but the 3d orbital appears down in the fourth row. It's one row down. So what's going to happen here? We're going to put a down electron here, and you'll see why I'm doing this in pencil in just a minute, because we're going to need to erase something. And now we need to get over to copper. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's do this in the proper order. So d orbital, 3d, comes before 4p on the Aufbau structure. So it's an up arrow, up arrow, up arrow, up arrow. Another one. Now we go back and we start pairing up down, 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 and down. That's 9 electrons, and that should be copper's configuration. But if you read your notes carefully, and I mean all the way to the end, you found that there's a note there. And it says if it is the fourth or the ninth element in the transition metals. So let's see what we're talking about here. The fourth element in the 3d orbital, scandium, titanium, vanadium, chromium. If it's chromium, or the ninth element, which is copper, then what it does is it's more stable if it can be the fifth element, or if it can be the 10th element. In other words, it likes to have, these elements like to have either a half full orbital, d orbital, or a fully full, all the way full d orbital. So in the case of copper, you can see it's 1 electron away from having a full orbital. So it wants to have a full orbital. It's just the way nature made it. It's more stable if it can have a full d orbital. So where does it get that electron from? It borrows it from the 4s. So you take away this electron from the 4s. So instead of 4s having 2, it's only going to have 1. And you put that electron over here. Again, this is all in the notes, and it's one of the very few exceptions to the octet rule, but it is an exception to the octet rule. You don't need to understand anything more about it than this happens whenever you get to either the fourth, so that would be chromium, molybdenum, tungsten, or the ninth element, copper, silver, or gold. That's when it borrows an electron from its s orbital, from the s orbital in the same row, and then the s orbital is only going to have one electron. So let's go ahead and do this. It's 1s2. Then you go up to the 2s orbital. It's 2s2. Then you go up to the p orbital for 2. So that's going to be 2p6. Right there. That takes us to there. Now we're up to 3s2. You can see how this starts to get longer and longer as we go further down the periodic table. Now we're up to 3p6. Okay, and now the little tricky part here, we go to 4s, and the 4s only has one electron. There's the one electron. And then you don't go to the 4p, you go to the 3d. You just read the periodic table in the order that these appear. And that's going to give you 3d10. Now what about when you do get to the next element, which is zinc? You get one element past copper to zinc. Well, then the 4s gets its electron back. You would go ahead and place that next electron in the 4s, and then you truly would have a full 4s and 3d before you moved on to the 4p orbital. Okay, let's do the condensed. Now you're going to see the advantage of the condensed. Copper is right here. You go to the row before it, to the noble gas. That's argon up here. So you put that in square brackets. And now you just continue. And what you can do is, if you just want to symbolize it, you don't have to do this, is just go ahead and put square brackets. That's argon right there. Everything there is argon. Remember, when you fill up a p orbital, it's a noble gas. So now we just do the rest of it. 4s1 and 3d10. And that takes care of that. Okay, that was actually a tricky one to throw at you this early with this exception. There are not a lot of exceptions to the Aufbau principle like this. That's one of the few, and I wanted to be sure you saw it and saw that that could happen. But normally for most elements, you're just going to put them in the order that you see them. All right, let's finish this with strontium, and then we'll do some of these in class on Monday. So strontium is way down here in the fifth row. So we're simply going to do up arrow. We're going to fill up the first orbital. We're going to fill up the second orbital. Again, let's get in the habit of doing things in the proper order. So up arrow, up arrow, up arrow, and then that's Hund's rule, and then Pauli exclusion says that the paired electrons have to be in opposite spins, up and down arrows together. Okay, and again, you don't have to do this. I'm just doing it to emphasize the point. That would be neon. Right there at the end of this p orbital, at the end of this s. It's the only time the end of an s orbital is a noble gas, is the first row is helium. Okay, 3s, so we're now down to sodium, magnesium, up arrow, down arrow. Now you're ready to go up to 3p. So it's up, 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 and then down, 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 and the noble gas that represents is argon. Okay, now we're up down to 4s, up and down. So here's 4s right here, but you can't put the 4p electrons in because this d orbital comes before it, and since 4 has to have a p orbital before it has its own d orbital, that d orbital has to belong to the row before. D orbital always appears one row after its number. So this is the 3d orbital down here in the fourth row. So we're just going to do it the same way. Since we know we're going to fill this one because we're going all the way down to the fifth row, you could just fill it up, but again, get in the habit of doing it in proper order so you retain that. And then down, 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 and down. Okay? Now, is that a noble gas there? You're at the end of that, and the answer is no. You only have a noble gas at the end of a p orbital. These are not valence electrons. You may say, why not? They're the highest energy level electrons that we have so far. So assuming we stopped right here, which would be zinc, why aren't those valence electrons the highest up? They simply aren't. That's all you have to know. That's all you have to accept. They are not valence electrons. Okay, now we're ready. We finished the 3D right here at zinc, and now we're ready to do the 4p orbital. So we come here, and we know we're going to fill that up also. So up, 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 down, down, down. And what noble gas would that be? It would be the one at the end of the fourth row, which is krypton. And now we're at the 5s where strontium is, right there. So you have rubidium and strontium. So it's going to simply be up and down, and that's it. That will get you to strontium. That will be the electron configuration for strontium. Now let's write this whole big long mess out, and then we'll do it in condensed form, and it'll make life a lot easier. So the electron is 1s, 2. You fill the first 1s orbital. Now you go to 2s, 2. Now you fill it up all the p orbitals, so that's 2p, 6. Now you go up to 3s, 3s, 2. Now you go to 3p, 3p, 6. And now you go to 4s, 4s, 2. And now you got to go to 3d. That's going to be 3d, 10. And now you go to 4p. Now you will see some books and some places that will put the 4s and the 4p, 4s and then 4p and then 3d, just so they keep the 4s together. But that's really not proper. It's not the order that they come in terms of Aufbau. So you're now at 4p, 6. So again, that's another noble gas. It's the end of a p orbital. Here we are, and now we're up to 5s, 2. And that would be strontium. Okay, and then down here, condensed electron configuration. So what you do is you find your highest level noble gas. So there's a p6 orbital. P6 is a noble gas. So you can put this whole thing in brackets. And that would represent the noble gas that comes before strontium, which would be krypton. So you simply write brackets Kr. And then whatever's left over there, 5s2, and that's it. So that's a lot easier than writing that whole big thing right there. Okay, so that's it for the day 58 assignment. That's due on Tuesday. You might want to get going on the day 59. And that's going to get into a new subject. So finish this one up. We'll talk about this assignment and day 59 as well on Monday. Anyway, that's it. That concludes all the notes for this particular assignment. So have a good day. We'll see you on Monday.